Each of your groups had one problem to do in which you applied a combination of factoring strategies to factor a trinomial. And in both of them had the same kind of arc, where the first thing that you thought about was the greatest common factor method. Can I bring something out of each of the terms that's common to all three of the terms? And then after having done that, you ended up with a trinomial that you now needed to use a different method for. And in both cases, you were stuck using the AC method, because both of the trinomials that you got had a leading coefficient which was not 1. So let's take a look at the first one, 9x to the 5th plus 24x to the 4th plus 12x to the 3rd. Here's the work that's up on the board. So the first step was to look across these three terms and figure out, is there a factor that they all have in common? And one of the things that I notice happens is that people very quickly key in on the number, which is common to all the coefficients, the numerical factor, the 3 in my 3x to the 3rd. But sometimes people will forget about the x to the 3rd part, which is in common to these three terms. So what's the mental shortcut again? What's the quick way of looking across these three terms and realizing that x to the 3rd is the greatest common variable factor?
It's the least.
It's the least of all the exponents on the x's, right? That's always the rule of thumb. That's going to be the limiting reagent, right? It's like I've got hamburgers, I've got hot dogs, and then I've got buns. And whichever one of them I have the least amount of is the number of sandwiches that I can make, right? So x to the 3rd is then the least exponent, and so it becomes part of the greatest common factor. So using a lattice, you can bring that factor out and figure out that the missing factor is 3x squared plus 8x plus 4. And that trinomial we needed the AC method for, because it was a quadratic trinomial whose leading coefficient was not 1. One of the points I was making to this group over here is that the AC method is secretly the method that we're always using, even when the leading coefficient is 1. Just to pause here for a second. If the leading coefficient of this were equal to 1, then we would be asking, find me a pair of numbers which multiply together to give me this and which add together to give me that. But since this is 1 in the front, A times C is the same thing as just C. Right? So you can always feel free to think of the AC method as the AC method, even when the leading coefficient is 1. It just reduces to the same sum and product game that we always play. But here that leading coefficient is very visible. It's a 3. You had to write it yourself on the page. And so that mentally cues you that you know you want AC in this example. And A times C for this quadratic is 12. The linear term here is coefficient 8. And so we were looking for a pair of numbers which multiply together to give me 12, A times C, and which add together to give me 8, for which 6 and 2 win the prize. And this now is a step where it's easy to lose the tune. What do I do with that 6 and that 2? Well, what did you do with the 6 and the 2 in this board work? Where do they show up next? They show up in the boxes. They show up in the diagonals of this grid. So we're setting up this grid to factor this quadratic trinomial, the 3x squared and the plus 4. We know that we can just put those in their own cells, and they're going to factor themselves automatically once we figure out how to break apart this 8x and use its broken pieces to fill in the two remaining parts of the grid. So the 6 and the 2 really just did this. If I'm reading your grid here. It just broke the 8x into a 6x plus a 2x. Right? And then once we've written this out in 4 different terms, 3x squared plus 6x plus 2x plus 4, the magic of the AC method is that the first pair of terms have something really nice in common, 3x. And the second pair of terms have something nice in common, 2. And for both of those, the cofactor is the same, x plus 2. That's the magic of the AC method. Once you've used that 6 and 2 to split the middle term, then as soon as you figure out one of the greatest common factors of a row or a column in this grid, that lets you then fill in the remaining missing factors. 3x goes into 3x squared x times. 3x goes into 6x twice. And then 2 goes into 4 twice. And that lets us fill in this remaining 2. And then everything is all set up and we already have our answer. Not forgetting the 3x to the 3rd that we factored out in the very first step. We then have a factor of x plus 2 times a factor of 3x plus 2. One of the things I really, really like about this method of factoring is it builds in a check on your answer. One of the best ways in a factoring problem to check your work is just to re-multiply everything back out and just verify that you get back to the original problem. But having all the work so carefully organized into the grids the way that we have it here, we can use those grids to check our work. If it's really true that this multiplies together to give me this, then I should be able to go backwards and say, what is x plus 2 times 3x plus 2? Well, it's 3x squared plus 6x plus 2x plus 4, which is 3x squared plus 8x plus 4. And then when I multiply that by 3x to the third, I get these three things. So all I really have to do kind of to check my answer is just to check all 4 of these grid squares and all 3 of these grid squares just to make sure that they have the right products in them. And if they do, then we're all set. And so I agree with this answer. 3x to the third times x plus 2 times 3x plus 2. So our second example was very much of the same flavor. 9v to the 7th minus 33v to the 6th plus 30v to the 5th. Here's your board work. So it started in exactly the same way. Let's figure out if there's a greatest common factor among these 3 terms. And in this example, the greatest common factor was 3v to the 5th, and the missing factor was 3v squared minus 11v plus 10. Another case for the AC method, where in this example, A is 3, C is 10. And so in our sum and product game, the product that we're looking for is 30, and the sum, negative 11. And so here, negative 6 and negative 5 fit the bill. And again, honestly, this is the step when I was first figuring out how the AC method works. This was the step that always gave me fits. What do I do with that minus 6 and that minus 5? We use them to split that middle term. So we put them in the off-diagonal squares of our multiplication grid. And then factoring out the greatest common factor in one of the rows, so maybe we use this 3v squared minus 5v row. Observe that its greatest common factor is a v. Fill in the missing factor 3v minus 5, and then the missing factor between minus 5 and 10 will be minus 2. That gives me my complete factorization down here at the bottom. And again, we can check our answer, now that we've done it this way, just by checking the product in every one of the grid squares. Yep, 3v times v. Yep, minus 5 times v. Yep, 3v times minus 2. Yep, minus 5 times minus 2. Yep, 3v to the 5th times 3v squared. Yep, 3v to the 5th times minus 11v. Yes, 3v to the 5th times 10. Yep. So this must be the correct answer.